these questions are always interesting because it's a little bit tricky. It says Rob unloads a box in 5 minutes. So Rob does one box every 5 minutes. Whoops. Okay. So in 1 minute, so how many boxes does he do in 1 minute? Well, we divide both by 5. So he has 1/5 of a box per minute. That's his rate. So converting that to a rate is kind of something that is one of these typical standardized test things. Jen unloads a box in 3 minutes. So Jen is one box in 3 minutes. So if you divide both by 3, we get 1/3 of a box per minute. So if they work together, they get 1/5 plus 1/3 of a box per minute. If we have to add, we have to combine, get a common denominator to do that. So that's 3/15 plus 5/15. So it's 8/15 of a box in 1 minute. Or, if I multiply through by 15 now, it's 8 boxes in 15 minutes. Okay? So that's how many boxes. They can do 8 boxes every 15 minutes. It says, what information do we need to know they can unload all the boxes in 30 minutes? Well, we need to know how many boxes there are. And then we can determine in 30 minutes they could do 16 boxes. So if they have 16 or fewer boxes, yeah, they could do them all in 30 minutes. But this is kind of how we convert that information, one box in 5 minutes, into rates, and then we combine their rates, and we get their rate per minute rate rather than per 5 minute rates or something like that. We get it down to a per minute rate when we do problems like that. Nothing to do with Pythagorean theorem, but good math nonetheless. 40. 90 feet of fencing enclosing the largest area. Okay. Which of the following would have the largest area? Basically, you just have to calculate the area of each one of these different things. So a rectangle with a length of 30 and width of 15, you just take 30 times 15, base times height for that, so 30 times 15. Oops. Is 450 square feet. A square with each side 22.5 is 506 square feet. An equilateral triangle with side lengths of 30 feet. That's a little bit tricky because we really haven't done that, but actually that fits right into our discussion of Pythagorean theorem, so it's a really nice extension question. Let's do that. Equilateral triangle, side length is 30 feet. In order to find that area, we're going to have to drop that altitude in, right? We have to find the height of that triangle. That's Pythagorean theorem. We did this yesterday. We talked about how in an isosceles triangle this is split evenly. So I have to find this height. That would be 15 squared. Get the right numbers written. Thank you. 15 squared plus the height squared is 30 squared. So that's 225 plus h squared is 900. So h squared 900 minus 225 is 675. So h is the square root of 675. And 675 square roots. Oh, no. A 5 root, well, no. It's going to be bigger than that. Yeah. 225 root 3, or 15 root 3. So 15 root 3 for this height. So the area is 30 times 15 root 3 divided by 2, or 225 root 3 units squared. And we'd have to estimate that. 225 times the square root of 3. Try again. Times square root 3 is about 390 units squared, so it's smaller. And finally, the isosceles triangle, you'd have to do the same thing, and you're going to find out that it's smaller. The square is the largest one. But you'd have to basically work through all that. Interestingly enough, I think the best answer for that is probably a circle that has a circumference of 90 feet. Would probably be larger than any of those choices. But that wasn't one of the choices, the only of the choices that we had there. So it's a good application of our Pythagorean theorem. And we did a few problems like that. But that would be like a definite extension type problem. Find the area of an equilateral triangle where you have to set up the Pythagorean theorem and do that inside. That would definitely be an extension style question on a quiz or something like that. Be a good one. Other questions? Let's look at the converse of the Pythagorean theorem, which is what we did today. We know that in a right triangle, a squared plus b squared equals c squared. It also works the other way. If I have a triangle where a squared plus b squared equals c squared, that must be a right triangle. Pretty simple. I kind of call this my three bears theorem. Or, yeah, the mama bear, papa bear, and baby bear. Remember? You remember the story about the porridge being too hot and too cold and just right? It's kind of the same idea here. Okay? You'll see why in a second. If a squared plus b squared doesn't equal c squared, we still get useful information. In fact, we can find out if the triangle is obtuse or if it's acute. Basically, it comes down to this, and this is where the bears come in. If c squared is too big, it's obtuse. If c squared is too small, it's acute, because small is cute, right? And isn't that the whole way it works? No? Okay. And if c squared is just right, get where I'm going? I see what I did there? Just right triangle? Yeah. Okay, it's dumb, but you might remember it. It's just a kind of dumb thing that people remember. But that's really what it comes down to at the converse of Pythagorean theorem here. If c squared is too big, and again, we're always saying if c squared, if that hypotenuse is too big. And think about it this way. The legs are kind of a fixed length. We did this before with hinge theorem. The legs are a fixed length. If that third side is too long, that hinge has to open up wider, right? Obtuse angle. If that third side is too small, that hinge has to close down. Acute triangle. Or if it's just right, you get the right triangle. But how is c squared related? So c squared is too big, that's obtuse. C squared is too short, then it's acute. So like I said, just remember Goldilocks and the bears. And you'll be all set for converse of Pythagorean theorem. Let's actually look at it in practice. Here are some numbers. Let's find out. 6, 8, and 9. What kind of triangle is it? Well, 6 squared plus 8 squared, and we're going to compare 9 squared. 6 squared is 36, 8 squared is 64, 9 squared is 81. 36 plus 84 is 100, and this is 81. C squared is too small. What kind of triangle is it? It's acute. 2, 7, and 8. Well, first thing we should always ask ourselves, does 2, 7, and 8 even make up a triangle? Yeah, because 2 plus 7 is bigger than 8. So 2 squared plus 7 squared, 8 squared. So that's 4 plus 49 and 64. 53 and 64. Oh, this time c squared is too big. What's it going to be? Obtuse. 777. Do we even need to check that one? What kind of triangle is 777? It's equilateral. Equilateral triangles have every angle measuring what? 60. They're equiangular also, so it's that obviously is acute. All right? I really don't even need to do that one because equilateral triangles are automatically acute. 5, 5, and 12. Not a triangle. Because 5 plus 5 is not bigger than 12. Again, that's one of those, if you recall, where the 12 would be here, we'd have 5 here and 5 here, and no matter how we change the angles, these two 5s, the 12 is too long, and they're never going to touch. Right? Here's a tricky one. 6 root 5, 2 root 57, and 4 root 3. Oh dear. First thing I got to figure out is which one is the longest side. I don't even know which one is the longest side here. So let's figure that out. I'm going to have to figure out in my calculator, just estimating real quickly, 6 times the square root of 5. That's about 13.4. 2 times the square root of 57 is about 15.1. And 4 times the square root of 3 is about 6.9. So it does make a triangle, and 2 root 57 is my longest side, isn't it? So we're going to have to set up my Pythagorean theorem. So 4 root 3, and don't use the decimal approximations, we're just using them to figure out what the longest side is. We aren't going to use it in our equation because if it does wind up being right, it probably wouldn't exactly work with the decimals. So 4 root 3 squared plus 6 root 5 squared, we're going to have to compare to 2 root 57 squared. 4 root 3 squared. Remember, that means 4 squared times square root of 3 squared, or 16 times 3, which is 48. 6 root 5 squared is 6 squared times root 5 squared, or 36 times 5. That's 180 plus 30, so that's going to be 210. So 48 and 210 is 258. We're going to compare that to 2 root 57 squared, so that's 2 squared root 57 squared, or 4 times 57. And 4 times 57 is 228. Wait a minute, 36 times 5, I did that wrong. Nobody caught that? It's 150 plus 30, it's 180. So this is actually 228. Aha, it's equal. What kind of triangle is it? It's a right triangle. Yay, because it's just right. It's equal. See, you scoff at the Goldilocks and the Three Bears reference, but it works. It helps you remember. Don't make fun of it. It's functional. All right, that's a lot of the work today, but we could also go to our coordinate plane and check to see if something's a right triangle. So I've got points at 3, 5. Okay, I'm going to have to go 1, 2, 3, 4, 5, 6, 7. I got 7 of those. So let's go every 2 of my regular lines is 1. So 3, 5, there's 1, 2, 3, 1, 2, 3, 4, 5. So 3, 5 is right there. 1, negative 4. So 1, negative 1, negative 2, negative 3, negative 4. There's 1, negative 4. And 10, negative 6. 3, 4, 5. And 10 is going to be there. Negative 6, negative 4, negative 5, negative 6. Those are my 3 points, plotted carefully. Going to connect the dots. Looks like it might be a right triangle, but it might just be close too. How can I prove that that's a right triangle? There are actually a couple ways we could go about proving this is a right triangle. Anybody think of one way in the coordinate plane we could prove it? Count? Okay, how is counting going to help me here? Okay, but can I find the side lengths by counting? Yes and no, not really, because they're diagonal. We'd use, there we go. So we'd use a distance formula to find the lengths of the sides. And we could absolutely do that. In fact, I think that's the method that they want us to use. We use a distance formula to find the length of each side, and then use those lengths to see if the Pythagorean theorem works or not, if we get a right triangle. Can anybody think of another way that might be a little quicker? It won't tell us if it's acute or obtuse, but it would tell us whether or not it's right. Any thoughts on how we might be able to just determine whether or not it's a right triangle or not? No. Using the coordinates, using our, what not? Wait, when we work on the coordinate plane, distance formula is one thing we can do. What are other formulas we use? Midpoint and slope. How could slope help me show if this is a right triangle? What do you got? Okay, if I calculate this slope, and they're negative reciprocals, that means that those are perpendicular lines, right? So if I just check those slopes, I could check to see whether or not it's a right angle. Now, if it is, we're good. We're done. It's a right triangle. If it's not, we're going to have to go back and use distance formula to determine acute or obtuse. Slope won't tell us acute or obtuse. Okay? But slope will tell us if it's right. So let's check and see. The slope from 1, 4 to 3, 5. Well, I could just count that too. I could, since it's drawn, we could count that. From 1, negative 4 to 3, 5, it's the rise of 9 and run of 2. So this is up 9 over 2. From here to here, the rise is down 2 and right 9. The slopes are negative reciprocals. That means this must be a right angle. Yeah. You wouldn't use slope at all. You'd just use distance formula for all 3 sides. You'd have to do 3 distance formulas. One for this side. So for this side we get square root of 1 minus 3 squared plus negative 4 minus 5 squared. So negative 2 squared plus negative 9 squared, so that's 4 plus 81, so square root of 85 for this side. Okay? And then we'd have to do that for all 3 sides and then set up our Pythagorean theorem. So it's actually a lot more work to have to do it that way. Slope is really nice and quick, but again, it only tells me if it's right. It won't tell me if it's acute or obtuse. This will tell me if it's acute or obtuse. So I always, usually when I get a problem like this, first I check with slopes just to see if it's a right angle. Because if it is, I can save myself a lot of time. That's essentially what we're doing today. That's it. It's not real tough. Goldilocks. So your mom go home today and mom says, so what did you do in school today? Oh, we learned about Goldilocks and the 3 bears. Yes, you can tell them. And they'll say, what in the world is that math teacher doing? What is wrong with that person? Why isn't he teaching math? Well, yeah, it's math, because Goldilocks and the 3 bears is all about math. It's all about too big, too small, and just right. Yes, I did. I'm sure other people have used it over the years, but I've never heard anyone else use it. Yeah. Yes, I can. I think. Yeah, there are no really new ideas in the world. And people have been saying that for ages. Okay. See what I did there? So, again, we're in our book. This time, page 444, 3 through 25. Hold on, let me take a look at that real quick. I may modify and reduce the assignment just a little bit. Let's make it 3 through 25 odd. Okay? That's not what I did. But 3 through 25, we're going to make that 3 through 25 odd, unless somebody wants to complain about that. Anybody? And we're going to be concerned by 3 through 25 odd instead of 3 through 25. Okay, 3 through 25 odd, 27, 28, 36, and 38. In fact, I'll go on the website, 444. 444.
Okay.
I'll go on the website and modify that. So, first, I'll stop the podcast.